Hello, everyone, and welcome to Talk Nerdy. Today is Monday, February 19th, and I'm your host, Cara Santa Maria. Now, before we dive into this week's episode, remember, Talk Nerdyism will always be 100% free to download, and that is because of support from listeners like you. If you want to pledge your support for the show, just visit www.patreon.com/talknerdy, like these fine folks did, including Phil T. Bear, David J.E. Smith, Pedro M. Rosario Barbosa, Jeffrey Perez, Charles Payette, Jonathan Wright, Christian Jeffrey, The Honorable Husband, Jafe, Gabriel Felipe Jaramillo Gonzalez, Brian Holden, and Jeffrey Sewell. There's other ways to support the show. You can learn all about them by visiting my website, carasantamaria.com. Okay, guys, this week it's a good one. Actually, it's kind of one of my favorites that I've done in a really long time. I was transfixed, I have to say, like edge of my seat during this entire chat. So this week, I sit down with physics and astronomy professor, Dr. Clifford Johnson. He is at USC. He teaches undergrads and graduate students, but he also gives a lot of public talks. He's just an incredible science communicator. He does a lot of consulting for popular films. We'll talk about that in a bit. And he has a brand new book out. It's really cool. It's a graphic novel style nonfiction science book for non-experts. It's called The Dialogues, Conversations about the Nature of the Universe. So guys, without any further ado, here he is, Dr. Clifford Johnson. So Clifford, thank you so much for joining me today.
Pleasure to be here.
So we are neighbors.
We are.
Oh, I love that. And we just met, what would that have been, a few months ago now? 4 months? Yeah, just a few months ago, when you were a speaker at what was it, Phi Beta Kappa event?
Yeah, what is it? The LA Lightning Talks?
Yeah, something.
And Lightning Talks, that was it.
Lightning.
Yeah. And Lightning Talks LA.
And I had a giant... What do you call
gong,
that thing? Yeah.
The mallet.
A mallet
yes.
for a gong.
That was awesome.
You only had 5 minutes to talk and I gonged you. Wait, did you finish in 5 minutes or did I have
think
to
I was
you?
maybe... No, I think I was only about 10 seconds out.
Yeah, that's pretty good.
Yeah.
That's really good. And so, of course, you were talking about something that I'm excited to talk to you about today, which is not just physics, but the intersection of physics and kind of popular culture, approaching science communication in a really accessible way using art, all of these wonderful things that I love just so very much.
Thanks. I'm really excited to talk about it.
Absolutely. So you are a professor of astrophysics?
Physics.
Physics in general. Okay.
But, some of the things I do intersect with issues to do with astrophysics and cosmology. I work a lot on black holes, for example.
Okay, yeah. So that's very kind of traditional cosmology, but you also do like more, Earth physics, Newtonian physics?
I love that black holes have become so mainstream now that they're now thought of as traditional cosmology.
Traditional cosmology. I know, isn't that funny?
Not so long ago, it still was a question as to whether they existed or not.
Exactly. And now you're right, like almost every cosmologist dabbles.
Yeah.
They dabble.
You got to. Yeah. They're popping up everywhere.
Uh-huh.
The aspect that I work on is very much at the level that doesn't necessarily, although, we'll see, intersect directly with observational astrophysics, because it's more trying to understand how black holes work at the quantum level. And what's really going on with space and time at the quantum level is one of the big questions that I work on. So that leads me to worry about black holes, but it also leads me to worry about issues in particle physics. Where does everything else come from? The particles we're made of, all of that. What's the origin of all of that stuff? And then it then leads you naturally to cosmology, because that's another place where the physics drives you to need to understand the quantum nature of space and time. So black holes have become this perfect intersection between several areas of physics, particle physics, cosmology, astrophysics, because the physics drives you to have to figure out how they work at the quantum level.
It's so fascinating to me, the sort of intersection between, I guess we could say, theoretical and experimental physics, especially with regards to some of these issues in particle physics and then, of course, in cosmology, because there are some observations that can be made and some observations that are not observed. So they're not observations yet. Do you work from observational data or do you work more in a theoretical kind of way?
So I am someone who's maybe an additional remove from a lot of the sort of everyday experiments. We pay attention to all the different aspects, but in terms of what informs the next calculation I might do, tomorrow, what have you, it's not necessarily going to be the output of that experiment you heard about in the news, because there's a sort of issue that I'm working on, which is trying to develop the toolbox that we're maybe going to use one day in the future. It's like we're routinely using aspects of quantum physics and relativity now in everything.
Yeah.
But there was a time in the early part of the 20th century when those tools in and of themselves were still being developed on the page before they were even being applied to anything. Although, of course, to help develop those tools, experiments were very important. But a lot of the mathematics, a lot of how the mathematics and the physics work together, you just have to work that out and see what works and what doesn't. And you have to try things. And that takes sometimes decades.
So I hate to interject before we get to what you're working on. But so would that be, for example, like clocks, atomic clocks now? We used to keep time and we kept time pretty well, but we didn't have the tools to really be able to keep time the way that we now can keep time. Like what kinds of tools are you talking about that have really shifted over the past kind of century?
Well, let's just talk about quantum physics, for example. 100 years ago, it was still relatively in its infancy.
Absolutely.
Right? We were just about coming to grips with properly being able to describe how quantum physics tells us how atomic physics works, how atoms put together, which we now know, is hugely important for understanding not just the fundamental structure of matter and why things are solid, right? But it's also important if you want to design an iPhone, right? The electronics that's carrying my voice right now, we routinely design electronics that moves electrons around interesting devices that are really, really tiny. And we can design devices to exploit the quantum physics. If you don't know quantum physics, you can't make these devices, basically,
I see.
Right? So it's a routine tool that we use. And we use it also as a routine tool in understanding how the universe has evolved over time, right? In particle physics, what have you. But there was a time when we just needed to figure out what quantum mechanics was, how it worked, how to get predictions out of it, how to do actual calculations. So a lot of what I'm doing is analogous to that, in that we know that it will be important to understand the early universe and the structure of black holes and stuff like that. We'll need to understand quantum gravity, how gravity and quantum physics work together, but we don't yet fully have that toolbox working yet. So I'm sort of working a lot on the toolbox. Now, they're kind of spin-offs that sometimes come out of the toolbox that people are trying to apply to current physics.
Oh, okay.
And that's really cool. That's sort of just a part of the big quest to understand how space and time really work at a fundamental level.
So when I think about the big questions sort of that are still unanswered, because like you said, a century ago, there were many, and we were just starting to come to grips with the fact that black holes were theoretical, and now we have really good evidence to support that they exist. When I think about sort of as a observer of physics and not so much a participant, in the grand scheme of things, yes, I participate in physics every day, but not necessarily at a scientific level. I think of what existed before the Big Bang. I think of what was happening when the universe was opaque in those first, 800?
About 300,000.
300,000.
Between 300,000 and 400,000 years.
Okay. So what was existing, what was happening during that
dark
first
ages.
dark ages, because we don't have, good visible evidence of it. And then I think about what you mentioned. How do we square that circle between quantum mechanics and gravity? And lastly, I think about dark matter. Is that a good sampling of the big kind of uncharted questions in physics, or there's just so much more than that?
Oh, there's a lot more, but certainly in this area of physics, those are some of the big ones. Got to also have dark energy.
Dark energy,
right?
Yes.
The universe, we now know, seems to be accelerating in its expansion, which was really unexpected. So there's some additional component to how the universe works that we'd had turned off. We have lots of mechanisms that can do that on the page as a theoretical exercise, including Einstein. One of the first things he did was discover a mechanism called the cosmological constant that can do that. But we don't know whether that's really what's giving rise to this accelerated expansion. if you turn it into a question of how much energy or energy density there is in the universe using E equals mc squared, it turns out that that's the biggest piece of the universe.
Dark energy.
Dark energy, right? So we're not really done if we don't really understand that. So you've got dark energy, you've got dark matter. And then you have, as we're learning now, there's some huge questions coming up about populations of black holes, because now we've begun to look at the universe in a completely different way than we have before, using gravitational waves, which you've probably been hearing about in the news. And black holes are colliding with each other, and we can hear the echoes in these gravitational waves. And so this is now giving us a new window on, well, how many of these black holes are there doing this? How often? And one of the big surprises already is the masses of those black holes. They're a lot sort of bulkier than were expected. So the question becomes, what gives rise to those kinds of black holes? Have they been around for a long time? Did they form recently? What are the mechanisms by which they form? It may turn out that there are a lot more of them colliding than we thought. So that might change our understanding of the evolution of stars, evolution of galaxies, all kinds of amazing questions that are suddenly exciting again because there's new input from data.
Yeah, it seemed like the scientists who, when, was it BICEP? When that was first turned on, were quite... No, LIGO. I'm sorry. When LIGO was first turned on.
Well, but there is BICEP as well.
BICEP was before LIGO. Yeah. BICEP was like several years ago. LIGO was 2 years ago?
So LIGO was looking for gravitational waves very, very directly.
Yes, between those two long arms.
Indeed, yeah. Two separate experiments that have those two long arms in an L shape called interferometers. And that's sort of, if you like, an entirely new kind of telescope. And as you've probably heard people say this before, historically, every time we come up with a new way of looking at the sky, it revolutionizes astronomy. It revolutionizes our understanding of the universe.
It creates an entire new field of physics. Yeah. Like there's a whole new crop of researchers who basically only do that and make millions of discoveries just based on that.
Indeed. It's a whole new way of seeing our world.
And I was so amazed when I read that when LIGO was kind of first turned on, and started to observe that, like, very quickly it has its first observation. And I think that maybe took some scientists by surprise. They thought, wow, what are the odds that this would happen so fast?
Those first few observations, there's a lot of great stories that actually a couple of books already have come out talking about them, which are, it's just sort of great serendipity.
Oh, yeah. Didn't Jana Levin write a book about
I was just about to say, Jana's book is one. There's another one that's come out, I think, in the last couple of months. And where there were some sort of, if you like, embedded reporters. But then it turns out that actually at USC, we're hiring right now, and we're particularly looking in that area.
Oh, interesting.
And so we've been hearing some of these stories from some of the people who've been involved, because they've been coming giving job talks and then telling us some of the backstory about, well, I just happened to be working late that night, and then the alarms went off. And then I called so-and-so, and then what have you. So there are some amazing stories. But the LIGO story is really amazing, because LIGO's been around and has been running for a long time. But what they do is they gradually, when they got the money, when they got more support from NSF, they could upgrade the machine. So they first needed to sort of show that the machine worked in principle, knowing that they'd turn it on, they wouldn't see anything because the physics would say that this, it's not sensitive enough.
I see.
But they need to sort of work out all the bugs.
Yeah, make sure it wasn't just getting every earthquake nearby.
Exactly.
And
figure out way. And then they just kept improving the technology to quieten down everything so they could listen more carefully, more accurately, improve their algorithms for searching. And then they'd upgrade. Then they got to this phase of what's called advanced LIGO. And they knew they were going to see something unless we really don't understand physics.
Yeah.
But I don't think anyone was expecting that. They turn it on, they're still tweaking, they're still, getting everything ready, and a signal comes in.
Yeah.
And that was their first event. I think it was, I want to say September 2015.
Yeah. Oh, gosh, it's been a while now.
Well, the big announcement, they had to really make sure, do the analysis. So the big announcement was January, I think, 2016. Time's flying. But since then, there's been even more amazing stuff. Right. And one of the most amazing things is that we're now seeing neutron stars colliding as well. Neutron stars are sort of these incredibly compact collapsed stars. They're not black holes. They're sort of, they're sort of on their way to being a black hole. and they're incredibly dense.
But they don't have the
objects.
gravitational kind of outcome of a black hole?
It's sort of what happens is that when a star in its lifetime, if it's massive enough, it'll collapse down when it runs out of fuel. And depending upon how much mass it has, it may or may not turn into a black hole. And what happens is that there are various pieces of physics that turn on that may stop that collapse.
I see. And the difference is that there's no like event horizon in a neutron star?
Right. Yeah.
Okay.
So what happens is that you can get various mechanisms that stop. And one of the last one before forming a black hole is mechanisms that happen at the nuclear level. You can get mechanisms that happen at the atomic level, and you'll get things that are called white dwarfs. But sometimes there's so much mass that physics can't stop it, so it collapses even more. But then there's some stronger physics that turns on at the nuclear level and makes a neutron star. It's like one big atomic nucleus that's like miles across. And but if the thing is so massive that not even nuclear physics can stop it, then it'll collapse and make a black hole.
Gosh, so I never thought about the fact that these things that are so big, that are so cosmic in nature, are defined ultimately by like tiny, tiny microphysics.
Yeah, exactly.
Oh, wow.
Yeah. So the strong nuclear force dominates in the operation of a nuclear star, and we would dearly love to know what the physics of the neutron star core is. So how do you learn about the physics of stuff? You take it apart, you look, see what comes out, what have you. Now, we can't take a bunch of neutron stars and do that here on Earth. Happily, nature does that for us. Neutron stars can collide into each other. And now they're seeing that in these kinds of experiments as well, the outcomes from gravitational waves.
Wow.
But the really cool thing, which is different from the black holes colliding, is that when you get those neutron stars colliding into each other, in addition to the ring in space-time, that's the gravitational waves, there's a lot of visible stuff happening all over the spectrum. So this is this new field now that's called multi-messenger astronomy, where you see perhaps with gravitational waves that these neutron stars have collided. You quickly call up all the observatories around the world and say, this thing has happened, train your telescopes on this patch of sky because you're going to see something amazing, and do all the measurements in all the spectra that your telescopes are capable of. And so what happens is that gives you multiple ways of seeing this single event, and it tells you so much more physics.
Oh, wow.
So that actually happened in summer of last year, the first, like a gold-plated, literally, and I'll say why, event, because the neutron stars collided. They had enough time to tell various observatories, including just here, Southern California, the Carnegie observatories in Pasadena were on it. They were able to find the place in the sky where that was happening, do lots of measurements, because then you're able to tell from the spectroscopy, from the kinds of light that come out in various, whether it be visible or gamma rays or what have you. You can tell what's going on with the nuclear chemistry. So that tells you a lot about what's being made in those collisions and what have you. So we now know from that probably most of the very heavy elements, for example, gold in the universe, in our jewelry, is actually made in neutron star collisions.
Oh, wow.
Which is just amazing.
So, okay, my alarm bells are going off, and this is probably a naive question, but what is the difference in time to travel between a gravitational wave, visible light, IR, UV? It seems like all those things would reach us at like years apart. Do they not?
They do not. They all arrive at essentially the same time. That is something that we knew on the page was probably true, in that all of these different kinds of things travel at the speed of light. But of course, that needed to be tested. So that gives you another test of that. So it sets limits on how much of a discrepancy those things would have. So we now know that indeed I can't quite remember what the limits are now, but it's down to one in several. I want to say of the order of 10 to the minus 13, something
Big,
like that.
Or small, sorry, very small, many
the
zeros.
Discrepancy between, One way of phrasing it is that in the trade, as it were, it has to do with the sort of the effective mass of the particle carrying the influence. So light is carried by photons. Light in all of those spectra, whether it be gamma rays or visible or infrared or what have you.
That's all photons.
All photons.
And
photon has zero mass.
Zero mass, okay.
And so it moves at the speed of light. So there was a possibility that the effective particle, if you like, the particle wave kind of thing, the effective particle associated with the ripples in space-time, gravitational waves, there was a possibility that it didn't have zero mass. And that would mean that it traveled more slowly. But in fact, that influence is coming from of the order of 1.5 billion light years away, and it's getting here around the same time. So if there was a discrepancy, it would have to be incredibly tiny.
So 1.5 billion light years away means that it happened 1.5 billion years ago. Yeah. Okay. More or less. Yeah. But that they're getting there. The gravitational waves are pretty much matching up.
Yeah, because over that distance, if there was a significant difference, that would add up to
years and years
and years.
Yeah.
So they're coming within fractions of a second of each other. That delay is probably the delay due to instrumentation, blah 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 blah, so on and so forth. It's not to do with the particle masses themselves. But what we do in physics is we put bounds on things. So this tells you now the mass of the graviton cannot be higher than X. X is really, really tiny.
Really tiny. Yeah. And so is it just that the event is so massive that it gives the physicist time to literally be like, Joe, put the telescope over there? How do we not miss it?
Yeah. So that's, and so of course, because no one was looking with regular telescopes in that patch of the sky at that moment, things were missed. The initial flash, as it were, which also has a lot of information, was missed. But happily, it takes a lot of stuff's going on. So it took some of that initial stuff. It was still glowing, as it were, quite a bit in the initial time when people looked at it. And it took a long time for the signals to decay. So people could really do a lot of astrophysics, a lot of spectroscopy. What they're doing right now, LIGO's down right now. They're ramping it up for the next upgrade. There's also the Virgo experiment in Italy. And these guys will all come back on in concert later this year. They're working out their protocols so that they're better now. There's more automation in the machine detects a likely event. It can triangulate because there's two components to the machine. There's also the Virgo thing. In later years, we'll have other ones. So they'll be able to more quickly say it's in that patch of sky. They'll be able to automatically send signals within milliseconds to other telescopes that'll automatically point and just start photographing that pointed part of the sky.
So basically those telescopes. See, this is what I love about science. I love this about science is that it transcends politics. It transcends personal kind of bias. Now, that doesn't mean that that's not fully there when you read scientific articles. It doesn't mean that, especially in more social sciences, that we don't have to think about the fact that people are doing the studies and people have their own, interests. But the truth of the matter is, when it comes to something that I think is fundamental to understanding our place in the cosmos, basically everybody's like, yeah, that's more important.
Yeah. Exactly.
Sure, you can hijack my telescope.
Exactly.
I may be from a warring country, but I do not care. I want to get this data with you.
And that's exactly what's going there. Working out the protocol. So no matter what those telescopes are involved in, if we could just have 10 minutes of time to look at that in this moment from your piece of sky. Because, if it happens in the northern hemisphere and you can't see it from the southern hemisphere, then those telescopes, we need to get everyone involved up there and then the other way around. So you need cooperation. You need as many eyeballs, literally and figuratively, on such events as possible to learn all of the physics. And so this is an amazing time for this multi-messenger astronomy is also great because it really forces everyone to cooperate for the greater good of the amazing science that's being seen. So it's just great.
You sometimes forget why, popular science writers, physicists who do what you do, who give a lot of talks and who work really hard to ensure that the conversation is had with everybody, not just people who are, in academia. You sometimes forget why there's so much passion. It's complicated and technical, and they're talking about things that happened billions of years ago, and I don't see how they apply to me. And then you have these conversations, and you start to get misty-eyed, and you're like, oh, crap.
Right. Yeah. I mean, people's eyes really light up when you tell them that thing that happened billions of years ago, a thing just like that is responsible for the gold you're wearing around your neck or what have you. And people really, oh my goodness. It all had to come from somewhere.
Absolutely. And I think that that's why when Sagan talked about how we are star stuff, that we are made of the same material that was forged in the furnace of a star. Like, it's just so meaningful to think about how the little bits that make up who we are really cosmological in nature.
Yeah. And that's another great example of what I was talking about earlier, actually. So remember, I was sort of talking about working out the tools of how a piece of physics works that will then later end up in everything. So we understood quantum mechanics. We understood how to describe quantum processes, various kinds of reactions happening at the quantum level, compute the rates at which stuff goes in and comes out, stuff like that, all seemingly very dry on paper. We worked out a lot of the nuclear physics that people hadn't really done experiments in yet, but sort of worked out the details. And then various people, principally a guy called Fred Hoyle, back in the 50s and 60s, began to realize that a lot of this stuff is going on in stars. And so he was actually the first to realize that a lot of the heavy elements had to be made in stars. And he worked out the details and discovered that, a lot of the stuff we're made of, the sort of medium heavy stuff that we're physically made of, is manufactured in stars, distributed in supernova explosions, and so on and so forth. And we're really made of star stuff because we had worked out the tools needed to then answer that kind of question, or even have the thought that that might be a question to have.
So what is that medium heavy stuff? Is that, when I think of what we're made of, I think of we're made of mostly carbon.
Yeah. So you have, the Big Bang was, an amazing cataclysmic event at the early universe. The universe is super hot, super dense, and then it starts cooling down. That did some of the early fusion, some of the first fusion. You have stuff like essentially the lighter stuff like hydrogen and helium and maybe some lithium and so on and so forth. But then the big question was, stuff basically wasn't at that high temperature and held together for long enough to, if you like, to cook the heavier stuff. To kind of coalesce into these bigger elements. Yeah. So that had to take place somewhere else. And the big question was, so where's that other stuff made? We know it exists because we're made of it and we can see it around.
Yeah, we measure it all the time.
Yeah. Where is it made? And then as we understood nuclear physics more and more and the processes, then you could actually start doing the kind of calculations that would say, well, how much of this stuff is produced given how many stars there are that we can see, and we can extrapolate how many more there are, given how many have these kinds of environments, given how many supernova events when stars explode and create this compression that can make more sort of cooking happen. And so then as we got better at doing the calculations, by we, I mean the field.
Yeah, many people.
I wasn't alive at the time. We got better and better at it till we realized that indeed, stars cook more of the elements up the periodic table or down, depending upon how you want to read it. But then there's a whole middle range. And up until recently, people thought maybe all of it was nuclear physics going on in stars, late burning stages of stars, and then the supernova explosion that a lot of stars do. And a lot of that stuff can probably be made in those stars as well. But the issue also is, what are the abundances? How much of this stuff is out there?
Whether it can make it is different than whether it does make the quantity that
enough
exists.
Of it, And so now stuff like, gold, uranium, platinum, stuff like that. To get those, the really good stuff, right? To get those sorts of abundances, now we have a new mechanism, the colliding of neutron stars, where they're able to really watch that stuff. I mean, they're literally watching that stuff forming from the light that's coming out. You can see what element. Stuff glows because of the kinds of chemistry associated with it. I use chemistry in a sort of loose sense to mean nuclear chemistry as well as, atomic chemistry. Stuff glows in a certain way that's called spectroscopy. So you can look at an object and see what it's made of by what it's emitting. So the spectroscopy is changing in this neutron star collision event as various kinds of elements are being produced in various abundances. So they could really measure what's going on, what's being produced. And then you extrapolate, given that we saw this neutron star event, we know the distribution of stars, what have you, you could say how many of these neutron star events happening around, and so how much of that stuff's being produced. And it roughly matches the amount of gold and stuff that we expect to be out there.
So crazy.
This now becomes the primary mechanism by which that stuff is made.
And of course, this is me trying to oversimplify everything. But when I think about the Big Bang, I think about probably one of the most energetic events in the history of the universe.
Well, it is the most,
It is, right? It's the one. Yeah. But it was fast.
Exactly.
And so is that the difference, that these lighter elements couldn't these heavier elements couldn't coalesce because there just wasn't enough time?
Absolutely.
Okay.
You need to hold the stuff together. So the reason stars work and are such amazing ways of producing energy that, we benefit from our sun, for example, is because they have a way of holding all that stuff together at that temperature for fusion to happen.
That's why you hear them called like nuclear furnaces.
Yeah.
Because they're just burning and burning.
Exactly. And the stuff that's holding it together is gravity. So stars become these great ovens for cooking stuff because, So you can hold stuff together with gravity. You also can get stuff to get close to each other in order to fuse if you collide them. And then you need to hold them long enough for a lot of those collisions to happen and stuff like that.
So it's like even more energy and a long time.
A lot, yeah, exactly.
Wow.
Yeah. A neutron star is like a giant atomic nucleus in the sense that it's a giant ball of mostly neutrons, right? So I'm sure you know this, but let me just
protons
recap.
and neutrons
exactly,
in the middle.
Right? Yeah.
Electrons
you've got
outside.
The fluffy stuff outside with these electrons. That's the domain of chemistry, blah, 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 blah. And inside, very deep down, 10 orders of magnitude inside, are these tiny things called neutrons and protons. And those are really densely packed together. But
and
an atom
when you
is
talk about nuclear physics, you're talking about what's happening at the nuclear level of an atom.
Exactly.
Okay.
Yeah. An atom is mostly empty space, right? It has this tiny nucleus and then this shell of electrons, what have you. And so we're mostly empty space. Right?
Weird.
Yeah, it's weird, but we're really mostly empty space. Now, imagine if you filled up all that empty space with neutrons and protons, or stuff that has the mass of neutrons and protons. So let's say all neutrons.
Yeah.
And you filled it up to 10 miles across. You would have this unbelievably dense thing. And that's what a neutron star is.
Yeah.
The folklore that you might hear is that if you took a teaspoonful of neutron star material, it would weigh millions of tons. It's that dense.
It's almost inconceivable because we're so used to the limits that are set by living on Earth.
Yeah, exactly.
But the universe
has awesome extremes. Yeah.
But of course, even just on Earth, you can look at the difference between a helium balloon and then, steel.
Yeah.
And you can look at the same amount of physical quantity and look at the difference in its density.
Right. Yeah. So that gives you an idea, but then you go several orders of magnitude, way more. Yeah.
Oh, it's insanity.
And then similarly, and then it's even more amazing when you get to black holes, right? You take something the mass of the sun or 10 or 30 times the mass of the sun, and you squeeze it down to the size of something the size of, say, New York or something like that, right? You have all that mass in that tiny space. That's what a black hole has in terms of density.
And at that level, physics gets weird.
It gets completely different from the kinds of physics we're used to. And that's why people like myself spend a lot of time trying to figure out what does that new physics happen? How does it play with other physics that we know, like quantum physics? So one of the big questions is, what's the interior of a black hole like? Because you can't avoid the quantum physics. There are suggestions that the interior of a black hole may be completely different from what Einstein's theory would tell us. Einstein's theory of gravity predicts black holes, that the simplest solutions of Einstein's equations from 1915 are the kinds of equations we use to model black holes and their collisions now. They don't tell you something definite about the interior. They only tell you about the exterior, and that's what we've been using in astrophysics. So the question is, what happens when you fall into a black hole? What happens when physics falls into a black hole? What happens to the physics of something that falls into a black hole? It seems, due to the famous Stephen Hawking, that actually quantum effects tell you that the stuff quantum mechanically begins to radiate back out very slowly for big black holes, but much more important for smaller and smaller black holes. So that tells you black holes are intrinsically quantum objects, and something gets really puzzling when you start trying to understand reconcile the points of view about what falls inside versus what comes back out.
Oh, so where's that boundary, and how does physics happen at that fuzzy boundary?
Yeah, exactly. And is that boundary sharp or fuzzy? And so there are all sorts of exciting techniques coming from that toolbox I was telling you about that I work on, other kinds of toolboxes, but largely this whole area of quantum gravity.
And so this was really some of the pioneering work of Stephen Hawking, and even of some of the Caltech physicists like Kip Thorne, right, who recently just won a Nobel Prize. Yeah, this was the kind of work that they were looking at.
There's sort of several directions you can go once you have a black hole in terms of what you do with it in terms of physics. Kip was and remains one of the drivers to go, let's look in the sky and see gravitational waves as a result of these objects colliding. So he spent a lot of time working on that. He's also done some amazing stuff in the quantum aspects as well.
I see. Okay.
But he's mostly known for, and if that was all, that would be way more than most of us. He's known for being the driver behind how to get LIGO running.
Interesting.
How to guess initially what the signals would even look like.
Yeah.
To even to see whether was it feasible to even look for those signals. He's one of the guys who was at the forefront figuring out those kinds of calculations.
And one of the biggest champions of making sure that this got off the ground.
Yeah, getting the funding. And
I guess I kind of knew that from talking to Jana, but I also just know Kip through his relationship with Steven as well. Because they're like best friends.
Right, absolutely.
And so there's a lot of lore, I think, around LA and around Pasadena.
Absolutely.
About the bets that they would make.
Well, there's just the big question of whether black holes existed or not. And these guys were around in that period where they were doing some of the work we all know now as part of our language, around the time when it was still a question. There would be entire communities going, why are you guys worrying about these things? They're just
theoretical
things on the page that may or may not exist.
Do you think that's how string theorists feel now?
Oh, yeah, absolutely. And so they were, laying bets about, well, when are we actually going to see those things in the sky? Do we already have candidates for what might be black holes, things like that? So there's a lot of famous bets you can read about in various books and what have you. And, there are physicists, I think, especially when you're in a point in the research where nobody knows what the right answer is. It's a great time to lay bets and challenge each other, and it ends up challenging everyone to do better work.
Yeah.
So it's kind of a fun thing to do, and it's very valuable.
So what are the kinds of bets that you're laying right now? Like, tell me a little bit about, and I promise we'll get to your new book.
But fine. This is way more interesting.
Tell me a little bit about some of the big questions that you're, doing your work to try to answer, and some of the places where maybe you think, I don't want to say feel, but you have good reason to believe that physics works one way when maybe other people have a differing opinion.
Yeah, well, I think where we are right now is an interesting time. So, and I'll talk about aspects that connect to some of the things we've already talked about. Back in this toolbox, we're trying to understand how to handle space and time at the quantum level. And black holes turn out to be one of the best test beds for this. So what you do, if you develop some new theoretical toolbox, like string theory, for example, it contains gravity, and it contains quantum physics. So one of the first things you do is, well, how does it handle black holes? What does it tell you? And we've had a number of remarkable results. Again, theoretical, but very important for the self-consistency of the theory.
Meaning that like the math has worked out really beautifully?
Not just beautifully, but consistently.
Okay.
And it matches other stuff we know from other approaches.
Oh, okay. Yeah. So you can still have corroboration within theory.
Yeah, absolutely.
Okay. All right. You don't need experimental evidence always to corroborate.
Well, you can corroborate the viability of the theory. Nature may still go, that's an awesome theory you have, but actually I'm over here doing something completely different. Right. So the way I tend to say it is, we know that string theory is a quantum theory of gravity. There was a time when people were saying, we're looking for a quantum theory of gravity. And I think most people say that. And I would say now that we know that string theory is a quantum theory of gravity. We just don't know whether it's the one nature cares about.
Yeah. And string theorists say the same thing. I've never met a string theorist who's, I did an episode of Talk Nerdy where I was lucky enough to moderate a panel with James Gates, James Sylvester Gates, Michio Kaku, and Brian Greene down in Texas, like last year or the year before. And I was really interested in how humble all of their approaches were. They're kind of like yeah, this might all be bullshit. But we have dedicated our lives to it because we feel like it's a viable option.
Absolutely. It's a viable option. I think there are a lot of string theorists who either because they're not being careful or because they really believe it, and either way is fine because there are many of us and we all have different opinions. They would say that string theory is a quantum theory of gravity and it's the quantum theory of gravity.
These three guys, they don't seem to have that opinion. They seem to have like it's one. And it's the one that works well enough for me to spend my time on it, but you never know if nature wants to play along.
Exactly.
Yeah.
So we have it, but there are camps out there who would say we still don't have a quantum theory of gravity, and would say string theory isn't a quantum theory of gravity. It's mostly people who don't really understand the theory, and that's fine.
That's fine because who really understands?
Or we have different views about what, different people define a quantum theory of gravity differently. And then some of that sociological, personal stuff can come in, blah, 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 blah.
Gotcha.
Great.
It checks some of the boxes, not all the boxes.
Yeah. But the point is that, in my opinion, the most honest way of saying it is, at least as we understood what quantum gravity was, years ago, when we first sort of started on this quest, string theory ticks all those boxes.
Oh, but there are new boxes that have come up.
Well, there's that, but it's just that we don't know yet how to test it against nature.
Exactly.
Yeah. So it might be one day we come up with a test and nature goes, no, those calculations you're doing in your quantum theory of gravity do not match how my quantum theory, the one that's out there in the world, actually works. Yeah. So the big challenge now, and I'm going to get to your question about bets and things, the big challenge now is to find ways of making actual predictions. And that's maybe very far away. String theory, as you just hinted at, is extremely difficult. We don't fully understand all of it yet. And it's notoriously difficult to pin down in terms of calculational predictions. And that's largely because we just haven't beaten it into shape yet.
And it really goes to the heart of that question that I read about. A lot of popular science writers love to write about this question of, is it that we haven't developed tools to measure the natural phenomena and match it against the theory? Or is it that some theories are fundamentally unmeasurable?
Yeah, and I would say, speaking as a scientist, that if you developed a theory that was fundamentally unmeasurable, you're not doing science anymore.
Interesting. So the goal would need to be that sometime in the future will be sufficiently advanced to develop sensitive instruments to do something.
It's not necessarily just sensitive instruments. I have this suspicion that there are things we are looking at right now that we don't even realize that they're sort of waving. Oh, yeah. They're clues waving.
Well, like gravitational waves, they're constantly just rolling past us. And not until 2 years ago could we really even collect them.
Well, that's sort of different. That was a sensitivity issue.
Oh, okay. Because we knew about
We knew about
Yeah,
we
that's
knew about
true.
Right, yeah. So there are things that string theory may turn out to be useful for. And I suspect this will be where the first signs, if string theory or something like string theory, or maybe even something nothing like string theory, but stuff that talks about quantum gravity in some way, whatever theory that is, I think the first stuff, and possibly the only stuff, that it begins to get right that makes intersection with observation won't be necessarily a direct prediction. It'll turn out to be better explanations for stuff we already know.
Gotcha.
And the explanations we already have.
Yeah.
And oftentimes that's how science begins, a new scientific field begins. You just find a simpler way. And that's all you can ever do in science, right? People talk about science being a quest for truth and what have you. And that's a nice way of putting things. But when it comes down to it, you're just looking for the best explanation at the time that captures as many phenomena in the simplest way.
You're looking for elegance.
You're looking for, if you also get elegance, that's a bonus, but so may or may not be. Yeah,
I'm envisioning this as a sort of mathematical theory, a description, an explanation, and every so often you have to throw in a constant. You have to add some sort of thing to square it up with the natural observations, and eventually, after enough iterations, you no longer have to square it up so much because the algorithm or the approach starts to actually be in perfect lockstep with nature.
Kind of. I think that's a nice way of putting it. You've touched on something very important there, which is getting parameters from nature. There's always things, in my opinion, and actually There's a chapter in the book that talks about this. There's always we'll always have to go out there in nature and measure some things and use them as input for whatever theory there is. One of the other problems with the sort of perhaps oversimplified things that people sometimes say in the media about some of this effort is that we'll one day just write down this awesome theory of everything is the phrase you hear, and then it'll just tell us everything, and then we're done. And really, the history of science is a little bit more nuanced. In fact, way more nuanced, right? In the sense that typically you write down this new awesome thing, but that awesome thing still needs input.
Absolutely.
There's still stuff that you can't calculate fundamentally in that thing. You have to go out and measure that. So you measure, the speed of light, you measure the strength of gravity, whatever it is that becomes input for that theory. And then given that input, you do a bunch of calculations and it tells you things that you hadn't thought of. Those are the predictions.
And so that's what those constants are. Because I always think of those as kind of post hoc things that you plug in to make it work, but that aren't measured.
It depends upon which constants you're talking about.
Interesting. Okay, right? So they vary in nature.
But at the end of the day, a theory of quantum gravity, maybe string theory, something else, I suspect will start beginning to give us a framework in which we could make sense of a lot of stuff that right now seems kind of random about the universe, or either random or we know it's not random, but we do not have an explanation for it. So, a famous example is when you start doing particle physics and you start looking, so we were down in the atom previously, right? And you've got the electron and you've got the protons and neutrons, right? And that's great. And you can figure out how these things work. Eventually you learn that actually protons and neutrons are made of things called quarks. And the kinds of quarks they're made of are called up and down quarks because of a failure of imagination to come up with better names, but fine. So you got up and down.
Quark is a pretty good
name. Quark is good, but up and down.
I know.
Really, guys?
We can't make it double amazing.
Well, it gets more interesting later. But so you got up and down quarks, you got the electron, and then there's the weak nuclear force, which is really important in medicine, for example, which gives you beta decay, and that helps you discover the neutrino, which is kind of a cousin of the electron, and that's great. And actually, you can describe a lot of physics, most visible physics that way. But actually, it turns out when you dig a little deeper, the electron has an identical cousin called the muon, which is exactly like the electron, but 200 times heavier. And it has its own neutrino that goes with it. And the up and down quarks have another pair of quarks that are cousins of them called the charmed and the strange quark.
So those are more creative.
Those are more creative. Yeah, right. So that's interesting. But then you dig a little deeper and you find that there's yet another family, right? There's the tau neutrino and the tauon, right? And there's what's called the top and bottom or truth and beauty quarks, depending upon who you talk to, right?
Ooh.
So there's these entire families that look exactly the same as each other.
They're just the bizarro version.
Exactly, right, yeah. There's actually no explanation for why that's a pattern, clearly, but it's not clear why that pattern exists.
Interesting. So it's definitely measurable. It's something we know is there.
Yeah.
We've got a lot of corroborating evidence, but...
And we have no explanation for it. And you could just go, that's the way nature is. Deal with it.
Yeah. How important is it to have a poetic description of why?
Right. And maybe we'll never have an explanation. Yeah. But if you had a theory that came along and began to explain and describe the phenomena we're already familiar with, but it also said, and also here's an explanation for that additional structure you're seeing there, or I could go into other places where that might be the case. It might be you could go if you're a skeptic, you could rightly go, well, that wasn't a prediction because we found that a long time ago.
Yeah.
And then I would push back and go, yeah, but you didn't have an explanation for it. Now you do. So it's not a prediction. It's sometimes called a post-diction. But I think things like that might be the early signs that you're on the right track for a new theory being viable, even if you don't necessarily directly create an experiment that collides vibrating strings and see vibrating strings come out. So the whole business of predictions and experiments and what have you can get very subtle, and it doesn't necessarily all come on at once. So I'm way off track answering the direct question you asked me, which
I
is,
love it.
What is it we're talking about now in
your lab? Like, what are you doing?
That people are maybe laying bets about.
Yeah,
right?
yeah.
And I would say it's probably too early for bets, but people are, there's some excitement that maybe we're beginning to touch on some areas that may intersect with this toolbox we're building. So in string theory, as I was saying, you can bring black holes in, and you can see how string theory treats them as a quantum object. And we had over the last several decades some amazing theoretical advances. Mm-hmm. But one of the things that has come out of it are suggestions that the structure of black holes may be way different from what Einstein's theory tells us. So there's this whole area called the fuzzball description of black holes. And in some ways, what happens is that a black hole turns out to be effectively a black hole if you stay outside and throw stuff in, or if you collide them in the sorts of things that are giving rise to gravitational waves. But really, it's just a bag of fuzzy space-time sort of tangled up in a way that's very hard to describe, which is why people are still doing calculations. Mm-hmm. And it's called a fuzzball. So it effectively ends up being like what Einstein said from the outside, but inside it's way more complicated and easier to describe, though, quantum mechanically. Mm-hmm. So the quantum physics drives you to that. Now, and that may just turn out to be wrong. But one of the questions and one of the interesting things is that fuzziness is fuzzy all the way up to the horizon of the black hole. Now, one of the things that happens when black holes collide in real astrophysics is that those horizons really are crashing into each other and merging to form a new black hole with a new horizon. Mm-hmm. So this may be an opportunity to see if there are any hints of some of this fuzzball structure in these things that LIGO and so on and so forth are measuring. Now, it's a long shot, and it might be that the effects, again, are way too small. And it'd be the usual quantum gravity story, which is that we have this wonderful picture of how everything's supposed to work, but it's too small for you to see, kind of thing. So it might be that that's the way it goes. But, maybe if we could just understand how to do these fuzzball calculations better, maybe there are actually ways of making contact with what's being seen out there. Wow. So the money might be into whether or not in measurements with real colliding black holes, we're beginning to see how we deviate from Einstein's description of gravity. That would be awesome.
Is that where your money is?
My hopeful money is as opposed to my informed, because I've done this awesome calculation money.
Is it early in the betting?
My hopeful money is that, yes, either with this generation of gravitational waves experiments, or maybe the next generations that are going to turn on, including the space-based one, mm-hmm. maybe being able to directly see what happens when black holes ring at the end of those collisions may tell us some things that connect to beyond Einstein gravity. And that would be wonderful.
Is that something that you're actively working on now?
I've been thinking about other aspects of quantum black holes, but I've begun in the last, I would say 6 months or so to seriously think about whether there are things that, I could bring to the table to make that, to make that connection. It's an area that I think a lot of people are looking at and going, hey, maybe it's time for us to put aside some of the other stuff we've been doing, because there may be a question here that we should be getting involved in.
I love that a big part of your job is to seriously think. Isn't that amazing that that's what you get to do for a living?
Yeah, it is. It is great, and it's a privilege, and it's one of the reasons that I spend a lot of time giving back, as it were. And for me, giving back is appearing on shows like this, writing books, helping out, with science in the rest of the media and movies and stuff, to go, look, thank you, society, for being set up in such a way that there is a group of people who are privileged to get paid to think about stuff like this that may or may not be the cure for cancer or what have you. And so part of my thank you is, let's talk about science for everybody, education about science, telling you awesome things we've been doing with taxpayers' money as a result of this way society is set up. So that's why I wrote the book, for
yes.
example. Yeah.
What an incredible segue. So I want to touch on the book. I also want to touch on something that you mentioned, which was that you do work sort of consulting on popular science, or I should say popular films that have a science component to them. So what are some of the movies that you've consulted on before?
Lots of different things, movies and TV shows. I guess most recently, you'll see a lot of talk about wormholes and things like that in Thor Ragnarok. When I don't know if you saw Thor Ragnarok, and they get from one place to another, what have you. So I chatted a lot with Taika Waititi and his VFX and other producers on how that might look on screen, how they might be able to sort of consistently within the science rules of the Marvel universe, move around and stuff like that. So that's a great example where, as I often said, I'm not trying to sneak spinach into your milkshake. It's just that it can help storytelling be a lot more fun and a lot more interesting.
Oh, and it doesn't. It takes, I think, some of the pressure off the storytellers who are already, developing an entire world and oftentimes with new rules and new language and new characters. Right. And then if there's something that can actually be squared with physics that we understand, why not let the fantasy of nature tell its story instead of also having to make that component up as well?
Well, nature's better at it.
Exactly.
Frankly. I often tell people that filmmakers, but not just filmmakers, that yes, you can go and make up a bunch of stuff, but nature so far has always beaten us in terms of just how amazing and mind-blowing things can be. My favorite example of this is when people come up and tell me, oh, I loved Interstellar, which, by the way, was a movie that Kip Thorne originally first conceived, and he was science advisor and what have you. Okay. People go, I love Interstellar, and they start telling me about, I love the way they mix the fictional science with the real science, what have you. And the thing that always amuses me is that there are things in there that people think are fictional, and that's actually the real science. The most famous of which is of course when they go down to that water planet for a few hours and they come back and 22 years have gone by. And that's actually a real thing called gravitational time dilation, and it's hugely important, and it happens here on Earth as well, but not so extremely. And around some of the objects we were talking about that have more extreme gravity, you would get those sorts of effects. And so that's an example of, we wouldn't have dreamed of that. But nature came up with it. And so it's fun. What I often say to filmmakers is that I spend a lot of time working out the rules of our real universe and how that works. And so I'm actually very well equipped then to come and help you when you've made your own universe with people flying around with magic hammers. I can at least help you have the sort of self-consistency and the sort of flexibility within some sorts of rules that are useful for good writing.
Oh, that's so interesting.
That then allow you to tell a good story and not have people pop out of the movie because all of a sudden you're doing stuff that isn't consistent with what you did in the opening sequence.
So it's not always about making sure that their storytelling is consistent with our universe. No. It's about making sure it's internally consistent. And you have those skills.
Way more important, yeah.
Because you've spent so much time looking at the internal consistency of our own universe.
That's exactly. Thank you for getting that, because I think people still describe what science advisors do, and I think science advisors still,
I think I always described it that way.
Science advisors, most science advisors, I think, also don't realize that this is way more important.
Absolutely.
That it's all about, people think it's all about fact checking.
Or making it just like it is here.
Accuracy of the science. And the word science accuracy, you're setting yourself up to fail. And anyway, that's not necessarily an important goal in a movie about Marvel characters, right? So National Geographic did this awesome new anthology series where the first season was all about the life and work of Einstein.
Now there, you worked on Genius?
I read every script. I taught them all the relativity and stuff that you see on screen. Well, they taught themselves a lot too, but I taught them all the stuff. I helped them choose chunks of dialogue and ideas that would interweave his life with the science. There, I was going for as much accuracy as possible.
Absolutely.
And I also happen to know a lot of the history, so there I was trying to help them get that right.
Oh, were you so pleased with how it turned out?
They did such a great job. I couldn't believe how much, because I'm used to giving pages and pages of notes on a script, and then they take, a couple of things. Yeah. Not so this case. there were chunks of dialogue that I wrote as an example of how these two scientists might talk about this, and they just sort of took that and dropped it in.
That's incredible.
Polished it up a bit because, they're the real writers. But I'm sitting there watching this thing, and these people are speaking some of my words.
That's
this is amazing.
And they're such good actors,
and they're such a great cast.
Bringing
and
it to
so
life.
forth. So, you bring different aspects of the science advising out depending upon what you're trying to do. There are other things I've worked on where the science is probably going to be a mess, but I'm still pleased because they got the scientists right. Mm-hmm. How that scientist as a character would behave, because they're informed by the scientific process or what have you.
Yeah, that's I think, one of the biggest failures.
Than just getting a bunch of facts right.
Absolutely. I think some of the movies that make me the most, like, the ones that are the most heinous are the ones where it's the scientists themselves doing things that a scientist would never do, like not exercising caution or like making decisions based on emotion, like, and just completely ignoring the evidence.
A chain of logic just breaks because it serves the story not to and what have you, and things like that. So, so I do a lot of that. And I happen to think it's a service.
Yeah, absolutely.
And so
it's incredible. All right, so I've kept you for so long, and there's still 2 more things we have to do. So we're going to dive right in. You wrote an incredible book. It's called The Dialogues: Conversations about the Nature of the Universe. And it's not just a book. It's like a really interesting, graphic, not so much novel. What would you call it? It's a graphic.
The problem, and we could go down a rabbit hole here, but the term graphic novel is problematic.
Yeah.
But it's known to be problematic in the graphic novel world.
Interesting.
Well.
Okay.
And so I've just learned to go with it and call it a graphic novel.
Okay.
Because,
because it fits most of those boxes.
Well, is Fun Home a graphic novel? Is Persepolis a graphic novel? These are actually biographies, memoirs. They're not really novels in the prose sense of the word. That's not and never what graphic novel ever meant.
Gotcha.
If you like, it's if you want to be pretentious about it, it's storytelling, it's narrative with using sequential art. And that narrative could be about anything. So it could be an adventure story or a piece of fiction, what we normally associate with a novel.
Yeah.
But it could also be talking about a set of concepts. It could also be talking about someone's life, someone's biography. So there are a lot of, among the most famous graphic novels, they're not really novels in any sense of the novel. So I'm making this worse by pushing on the idea that we should have more non-fiction graphic novels.
Yeah.
You see, for a while I tried graphic book, but then that has other connotations
or
that confuse
comic book.
people. Well, comic book, yeah, but the problem with comic book is then people outside the comic book world look at comic book and they're thinking that it's a Sunday funnies.
Yeah, that either it's funny or it's for children.
Yeah, exactly. Yeah. And so that's a problem. So there are just lots and lots of problems with how, I can even talk about this thing, or I carefully talk about it, but then, someone just goes with one thing and it's sort of,
So to be clear, it looks like a graphic novel, a comic book, whatever. It's art that has that very kind of comfortable and recognizable vibe to it, right? It's the different, what are they called? Cells? There's a name
panels.
for it. Panels,
right,
yes. It's got the different panels.
Exactly.
Some of them have dialogue, some of them don't.
Right.
But the story here, in quotes, is actually conversations about physics.
Yeah, like we're having right now, right? And so, if you like, the elevator pitch, right, is that you're an eavesdropper on conversations about science out there in the world between ordinary people. Because I realized some years ago that that's a thing that happens, but there's no real record of it. There's no book out there that celebrates that kind of conversation. And I think it's hugely important because I think we should be doing that. If science is truly part of our culture, which I think it should be, not just this sort of weird thing that special people do,
that we don't understand,
that we don't understand, but they'll take care of it and they'll make those decisions for us. Instead, it should be something that belongs to all of us, not just the scientists, not just the specialists. And the stuff that belongs to us in the culture, we talk about it all the time, right? So I'm sort of celebrating the idea of the conversation by simply writing a bunch of conversations and inviting you as a reader to eavesdrop on them and to almost feel like you're part of those conversations and then go out there and have your own conversations.
See, we're kindred spirits, you and I, because I feel like that's the entire purpose of this podcast.
Yeah, basically, I should have done a story about such a podcast. Well, there's always volume 2.
Exactly. It's all about having conversations with people who are knowledgeable about certain topics, but in a way that's accessible so that, and this is the best feedback I get from Talk Nerdy, is so that people then later go out and continue the conversation.
Yes. That's the key thing.
It's the important, it's the most important, it's the only important part.
Yeah. And just feel that they have permission, although they shouldn't need it, that they have permission to just dip into that.
Absolutely.
So talk about, I don't know who's getting married to who in the royal.
I don't know.
I don't
you
remember the names.
Know.
I should know, but I don't. Some prince is marrying somebody from LA. I don't know. That's great. It's an awesome thing. And then right in that same breath go, and by the way, have you heard that 2 neutron stars colliding have been discovered, and isn't that awesome?
And isn't it cool that our gold comes from
that? The gold that'll be in that wedding, all over that wedding, all the bling in that wedding was made in one of those collisions, right?
I love it. That is going to be in volume 2.
Well, that should be in volume 2. I will not get it out in time for the wedding, but
there will be another
other weddings will happen.
Oh yes, yes.
So that's it.
I have to ask, how long have you been away from the UK?
I've lived in the US, this time round for the last, 14 years?
Okay.
So,
all right. It's a good excuse. But something tells me you weren't always the biggest monarchist anyway. That's neither here nor there. Well, it's such a fun book. It's so cool. I love that you're able to, do your travel now, talk about it, bring it to people, and that it's so accessible for people to be able to look through. I think it's something about having the visuals really makes it like a faster and more, a page turner kind of read. It doesn't feel so dense because it's not like reading a script.
Right. It really is. You can take your own time. You can go through it fast. You can go through it as slowly as you want to with a prose book on science, because there's a lot of stuff there in the visuals. And there's some Easter eggs as well, and so on and so forth. And then you can look at things in ways that you don't normally get to look at when you're reading nonfiction science book. There are things I can show you instead of just telling you. It's the old show, not tell. But then there's ways I can put ideas together on the page that allow you to consume them and approach them in your own way. That isn't always something that's easily done in prose. So it's not that there's anything wrong with prose books.
No, I mean, they're so important.
It's just that I think, especially in my field, we've not been trying out new ways of reaching out to people. And the world is changing. Why aren't we? And the people, there's an awful lot of people who will go to the science section of the bookstore and pick up that latest book by name your favorite prose book, scientist, author, who all awesome people. But there's a whole bunch of other people who are also excited by science, or they haven't even realized that they could be excited about science, who will not go to that section of the bookstore.
Yeah, it's true.
So what about them? We've not been talking to those people. I sometimes intersect with those people because I do a lot of TV stuff as well and what have you. And so I know that there are people out there who watch a lot of science documentaries who will never read A Brief History of Time. And it's not because they're dumb or anything like that. They just have a different way into the subject. And so same thing, the graphic novel or the graphic book or the narrative art, or whatever you want to call it, or the comic is a huge and important form in our culture that happily is growing. More and more people are reading it and realizing comics are not for kids anymore and what have you. More and more people are no longer sort of covering it up on the subway when they're reading the comic, right? Pretending they're reading the Paris
New York
Review
Times,
or whatever, right? So more and more people are coming to that. And so where are we? Why are we not there? And so that was part of the point. I should say there's a lot of comics out there that have science, nonfiction. This is not really in the style of those. There's a lot of sort of what I also very awesome, what I like to call explainer comics. And they're more sort of, here's a lecture, here's an adventure, and, it's maybe a little bit more sort of gee whiz about the science, more comic-y, if you like.
And they're also great. The like XKCD types or the PhD comics types. And that's also, they serve the purpose that they serve, and they're incredible as well. But
I was thinking that it's a big tent, and there's also room for, in the same way on your bookshelf might be, if you like, a serious nonfiction science book that you feel respectable being seen, read. this in some ways is, looking over your shelf there, you have a whole ton of them.
I'm noticing that there's like, a book by Robert Sapolsky, and then there's a book that's a dinosaur pop-up book. So I feel where you're going here.
But you can also have a comic book in the format that's just as serious.
Yes.
Although there's humor too.
Yeah.
But it's not it's not the sort of comic zany humor type stuff. And again, there's nothing wrong with that. People have got that covered. And
it's not monolithic. I mean, the truth of the matter is there are a lot of people in this world, and not everybody responds to the same type of art. Exactly. Not everybody responds to the same type of science.
Exactly.
Yeah. And we've got to try and reach everybody.
You've totally got it. Yeah. And one of the biggest problems I have in producing what is a genuinely new kind of product, which, has not previously existed, is that a lot of people have not been paying attention to it because they can't put it into a box.
Yeah.
It doesn't fit. Sort of, it's not A, it's not B, it's just not anything. They forget about it. So it's one of the things I'm trying to push on is that this is a new mode which we can use to reach people. And hopefully this will get more people making more books of this kind. And that would be really exciting because it would just fill out the landscape of kinds of ways you can get access to science. And I think it'll also then help on the other end, which is it will bring more people and more kinds of people to engaging with science, which is something I think we need to do a lot more of.
Absolutely. All right. Well, Dr. Johnson, I want to not keep you much longer, but I do close every episode asking my guests the same two questions. And I'm really interested to hear your answers.
Oh, my goodness. I know. I'm nervous.
I'm really putting you on the spot now. And they're kind of big picture questions, too.
Gosh.
So whatever context is relevant to you right now, this could be, big picture cosmology stuff, or it could be like personal stuff, whatever you want.
Royal wedding.
Yeah, royal wedding kind of stuff. I want to know, when you think about the future out there, number one, what is the thing, if you had to pick one, which is so cruel to make you do, what is the thing that is like most disconcerting? What is the thing that keeps you up the most at night, that you worry, that you're upset about? The thing that's you're not hopeful of. But then on the flip side of that, so we end on a positive note, what is the thing that is the most kind of optimistic for you about the future? What are you really excited and just feeling quite hopeful for?
Oh, gosh.
Right. I know.
So,
cruelty.
Okay. On the first one, it's a mixture of things, but I think some of the big themes to do with the way our culture is, if you like, taking the easiest path, the steepest descent, as it were, means that doing difficult or perceived to be difficult things becomes less important. It becomes less cool. It becomes easier to avoid, as it were. So what that translates into is either intentional or unintentional anti-intellectualism, right? And this can feed into every fabric of what we do, right? So on the one hand, yes. So this book, for example, is all about, let's have conversations about science out there in the world just because it's a fun part of our culture. And that's a push against the sort of, if you're into a thing too much, you're a nerd kind of attitude, right? And it used to be just about science, but now it's about anything, right? You can be a nerd about just being interested enough to open a book or to Google a thing and learn something a little bit more than, and that's not good.
No, you can be a car nerd, a coffee nerd, a space flight nerd, so because you have passion?
Because you care about it, right? So it's like caring enough to put the effort in to learn more than the superficial stuff.
Yes.
So to give it a term, it's kind of an anti-intellectualism, but then it feeds into things that I think are really very dangerous in terms of how we organize ourselves as a society. I grew up fixing stuff. It's one of the reasons I became a scientist. So I didn't just fix things that were sort of obscure things that you didn't care about. It was the stuff around me, right? So it started with radios and old cameras and what have you. We're designing things, the stuff we all love, the cool tech that we really love. A lot of it is designed to make it harder for you to go in.
It's true.
And fix that.
Yeah, I can't open my iPhone or my laptop. I can't even replace the memory in this thing.
It gets harder and harder. There's ways to do it, but it becomes harder and harder. And of course, it fits with two things. First of all, it helps those companies with their bottom line. They'll tell you it's because, we're trying to make it thinner because that's what you asked us for. And so now we have to glue all this stuff together. It's not clear that that's entirely true. Why did you make all the screws really hard to unscrew and stuff like that? Yeah. It fits with that, but it certainly fits very nicely with this anti-intellectualism. right? And the consumerism.
Yeah, we don't need to know how anything works.
We don't need
I
to know
just
how
buy
anything
it
works.
and it's magic.
Yeah, exactly. So that whole thing, it's hard to see how we're going to come away from that. But it feeds into everything, and it feeds into all the other concerns, like in the environment, what have you. All of the stuff that makes us stuff, we're just throwing it away. Yeah. We're not recycling it because we're not fixing it. We're just buying new stuff. So that's a huge thing that bothers me. But then it's one of the symptoms, worst outgrowths of anti-intellectualism. But then it feeds into where we are politically and so many things.
Absolutely.
So that can be really depressing.
Yeah.
And it's one of the reasons also I'm out there doing my bit to go, hey, let's get excited about things going on in pursuits like science and so on and so forth.
And I think that it's so noble, because I think that there are scientists out there who, and again, I mean, not to denigrate, because it's completely understandable, but there are scientists out there who have the same kinds of concerns and fears and worries about kind of the direction that the kind of educated world is headed into. And instead of digging deep and diving into that pool of sort of difficulty and despair, it's like, I'll just stay with my people.
Yeah.
Because at least here I'm stimulated, and at least here nobody is denigrating getting a college degree and saying that that's that's snobby.
Right.
If I just stay here with my people and I don't talk to people who disagree with me,
right.
I don't have to worry about it.
Right.
And so I think it's really a noble thing, because it's not easy always to go out into the world and have conversations like this with well-minded and well-meaning people who simply are products of a system that is not in a good place.
Exactly.
Yeah.
Exactly. Yeah. I've never been called noble before. So thank you. Right.
Of course.
And then on the positive side, I think some of the things that are going on in the scientific world, not just in physics, but in many aspects of the world, that are really just new discoveries, yes, but the increased importance of science being, as it always was, a collaborative pursuit. That it's not about the genius locking themselves away in the tower and revolutionizing the world on their own, which actually never really happened. But it's collective in its way. And perhaps the growing realization for that can help more people get excited about science and feel, hey, I can be a scientist. I can contribute to science. It isn't about some extraordinarily being off scale in some particular set of tasks, what have you.
Or being into something that's super esoteric that I can't comprehend.
Yeah. And the growth of citizen science is part of that, and that's hugely exciting. I just think the fact that we can all, whether we have the training or not, we can contribute in a collective way to a scientific endeavor is a wonderful thing.
Absolutely. Well, gosh, Dr. Johnson, thank you so much for joining me. This was so much fun.
This was fantastic.
Right?
Thank you. And thank you for this important service, this noble service that you do in this podcast, and not just this podcast, but so many other things that you do that are just out there in the world, getting people excited about knowledge. That's an amazing thing. So thanks.
Yeah, it's just, I have the best job in the world. I can't complain. It's an awful lot of fun. But one of my favorite parts of it is getting to have deep dive conversations where we're able to get into nuance, where we're able to go off on tangents. I work in television a lot, which means I speak in sound bites a lot. And it's just so fun to be able to throw off those kinds of shackles and have real conversations.
Right.
So I appreciate you being here. And everybody listening, thank you for coming back week after week. I'm really looking forward to the next time we all get together to talk nerdy.